This is the last. We talked about definition of pressure, how it is defined, and various units, different units which are used to measure the pressure. Right. Now we'll introduce one more thermodynamic property. Name it as the specific volume. So we'll be using symbol small v to represent specific volume. So note down definition of specific volume. So it is basically the volume per net mass of your system. So the SI unit for the specific volume will be meter cube per kg. So we know that density is mass per unit volume, whereas the specific volume is going to be volume per unit mass. So it is basically the reciprocal of density, right? So using the limits, you can define the specific volume in this way. That small v is limit delta v tends to delta v dash. You know what is this limiting volume, delta v dash of delta v by delta m. And you should note down this conversion. 1 liter is 10 raised to minus 3 meter cube, because we'll be using this while solving numericals. So note down this relation. Can I go to next slide?
Yes, sir.
So you might be knowing about the temperature scales. Do you have any idea about what are different types of temperature scales? You must have studied.
Celsius, Fahrenheit, Kelvin.
Celsius, Fahrenheit, Kelvin, and Rankine. So these are the 4 scales. So look at the diagram on the left hand side. So we have 4 scales. This is degree centigrade, then the Kelvin, the degree Fahrenheit, and the Rankine scale. Out of these 2 scales, Kelvin and Rankine, they are absolute scales. And there is only one reference point. Whereas for the temperature scales having degree C and degree Fahrenheit, the 2 reference points are there. So these are called as relative scales, degree centigrade and degree Fahrenheit. So what you can see is on this thermometer. So this is the absolute 0, right? So the absolute 0 is on the Rankine scale. So the same will be matching with the absolute 0 on the Kelvin scale, right? And if you see the other reference point here, 273.16 K, this value, and this 491.69, this value, these are on the Rankine scale, right? Now what are the corresponding values on the degree centigrade scale and Fahrenheit scale? So 0 on Kelvin scale is equivalent to this temperature minus 273.15 degrees C, and this triple point of water is nothing but 0.01 degrees C on the Celsius scale, and the same is 32.02 Fahrenheit on the degree Fahrenheit scale. So you should remember, in case of absolute scales, we have only the one reference point, that is this the triple point of water, right? And the lowest temperature, possible temperature on absolute scale is 0, right? You cannot have the temperatures below this 0. Okay, so you can note down what are the relationship between the temperature in Kelvin and degree C, then the Rankine and the degree Fahrenheit, Rankine and the Kelvin, and then degree Fahrenheit and degree C. So note down these 4 relations. They will be useful while converting the temperature from one unit to another unit, right? So you will observe in even higher semesters, we will not use this value, exact value of this 273.15. So most of the time you will find that while converting temperature from degree centigrade to Kelvin, people only add 273 value. So this is some sort of approximation. This 0.15 term is ignored, or it can be neglected safely. So this will also give you the fairly accurate results. That's why people do not add the exact figure 273.15, rather they add 273. So you should not be surprised if I use this value later on. So note down these 4 relations, and then we'll go to next slide. We'll talk more about what is absolute thermodynamic temperature scale. So this Kelvin scale and Rankine scale, as I said before, these two are the absolute thermodynamic temperature scales. We'll talk more about the thermodynamic temperature scales in the topic of this second law of thermodynamics. There we will again come back to the this topic of the temperature scales. That time we'll see the further details. So time you just remember there are 4 scales: degree centigrade, Kelvin, degree Fahrenheit, and Rankine scale. And these are the relationships how to find out the temperatures. Now can I go to next slide?
Yes, sir.
Now we'll talk about the zeroth law of thermodynamics. Zeroth law of thermodynamics. Now see the definition of the zeroth law of thermodynamics. So when a body A is in thermal equilibrium with a body B and also separately in equilibrium with body C, then we can say body B and C are in thermal equilibrium with each other. Once again you read the statement: when a body A is in thermal equilibrium with a body B and also separately in thermal equilibrium with body C, then B and C are in thermal equilibrium with each other. It sounds something like if A loves B and if A loves C, then B and C they love each other. It is something like that, right? But however, it may not be true. We will come to know. So you should note down that zeroth law is the basis of temperature measurement. Zeroth law is a basis for temperature measurement. Now the schematic representation of zeroth law is given on the screen. So try to connect that statement to this diagram. So when body A is in thermal equilibrium, when body A is in thermal equilibrium with body B and also separately in thermal equilibrium with body C, then we say that body B and C are in thermal equilibrium with each other. So that is what zeroth law of thermodynamics is. And when we say that zeroth law is the basis for temperature measurement, what we mean is the thermometer is used as the third body. Right? So it means there is actually no requirement that if I want to know the temperature of these two bodies, B and C, I need not have to bring these two bodies in contact with each other. It is not required. Right? Are you getting my point or not? So what you can do is you have two bodies like this and you introduce just one third body, which is thermometer. So what your thermometer reads is the equilibrium temperature of these two bodies itself. So this is how the third body is replaced by the thermometer. That's why zeroth law is the basis for temperature measurement. Are you getting my point or not? Hello? Yes, sir. Okay. So look at your skin itself. Huh? See, the tissues which are lying below the skin, they have certain temperature, right? So let us assume that is a body, one body. Then your skin is the second body, and if you touch the skin by the thermometer, your thermometer is the third body, right? Get me or not? So your skin is in contact with the tissues, and it is also in contact with the thermometer. So what thermometer reads is basically the temperature of the tissues and in turn temperature of the skin itself. So that's why thermometer basis for temperature measurement is the zeroth law of thermodynamics. Clear?
Yes, sir.
Yes, sir.
Okay, fine. Moving further, we'll define work. Before we look at the definition given on the screen, tell me what is the definition of work from engineering mechanics point of view? You must have studied. So what is the definition of mechanical work?
Force into displacement. Displacing the body by applying some force on it.
Displacement, or what you can say, if you have force applied and your body moves a certain distance, right? Then you can say that the work is done, right? Correct?
Yes, sir.
So force into distance node, you can say it is the work, mechanical work basically. Now how to define the work in the context of thermodynamics? So we'll call it as a thermodynamic work then. Fine. So look at the definition on the screen. What is work? So work is said to be done by a system. Now these words are important. Work is to be done by a system if the sole effect on things external to the system can be reduced to raising of the weight. So this is our definition of work. So work is said to be done by a system if the sole effect on things external to the system. So I have a system like this, and the sole effect done external to this system, can be reduced to the raising of a weight. Then I will call that the work has happened, or thermodynamic work is there. Fine. Now I am going to project the diagram on the screen, and you have to find out whether there is some work involved or not. So what do you see on the left hand side? So we have a battery motor arrangement. So there is the electrical torque wheel. This is connected to the motor, and there is a fan which is attached to the motor, right? And you can see the system boundary shown by the dotted line, right? And whatever is outside the dotted line is surrounding for us, right? Correct? And now you can judge whether whatever the effect, sole effect, external to the system, is it represented by, or is it reduced to the raising of the weight? So we have to answer this. See, the sole effect external to the system is what is happening outside the system. Can that all effect be reduced to raising of the weight? So this is what we have to answer. So the question which we need to answer is this work equivalent to raising the weight? So whatever work is done by the motor on the fan, this work, is it equivalent to the raising of the weight? So this is what we want to do? No. So it means we have to replace this fan arrangement with some another arrangement where we can raise the weight, just like this. So if you look at the diagram on the right hand side, what we did is we replaced this fan by pulley and weight arrangement, right? Now this pulley is driven by the shaft which is connected to the motor, and now you can raise the weight, or you can lift the weight using the input from the battery to the motor, and motor in turn will help us in raising the weight. So this is definitely the work, right? So we have reduced the entire effect which is happening around the outside the system in the form of raising of the weight using this arrangement. So this can be called as a work. Is it clear?
Yes, sir.
Okay. Now you should note down what is the sign convention we are supposed to follow throughout the course, or throughout engineering you will follow same sign convention unless or until you are using the books written by the English authors. So if you refer maybe let us say 100 books on thermodynamics, you will find in 99 books the same sign convention is used, and only one book you will find where the sign conventions are used in opposite sense. So let us follow what people are following largely, right? So this is the sign convention we will follow, no doubt. So we have a system, like this and the surrounding, and this is the work done by the system. So this is by the system. Outside arrow indicates this is work done by the system, and this arrow indicates work is done on the system, right? So the sign convention is work done by the system will be treated as positive, and the work done on the system will be treated as negative. Note on this sign convention. Done?
Yes, sir.
Now we will introduce the most common type of work used widely in our course, that is PDV work or displacement work. What is displacement work? So look at the diagram. You need not to draw this. I am going to upload all this stuff. So let us say we have a piston cylinder arrangement, the way it is shown here, and there is gas enclosed here, having the pressure P1 and the volume V1. Now this is the initial state of your gas. So initial state is denoted by 0.1, and what is done is you can move this piston in the right direction, and this gas will expand, and this piston will reach this position 2, and the final state of the gas is described by the state point 2, right? So the properties at state point 2 will be repeated, the corresponding pressure and the volume, right? Now this is plotted on a PV plane. So I am taking pressure on the y-axis, volume on the x-axis, right? And this is your initial state 1, and the gas is expanding. So because of the expansion, we know that the pressure will decrease and the volume will increase. So we reach to the state point 2 here by the expansion of the gas. So pressure is P1 here, volume is V1, pressure is P2, volume is V2, right? And now we want to find out what is the work done in this process. Nothing but PD. Hello, can I go to next slide?
Yes, sir.
So what we are going to do is we are going to use the elemental approach, which is known to you from your mathematical background, right? So I am going to select an elemental strip like this, elemental strip having thickness dV, and let us say the pressure at this location of the strip is P, right? And the idea is I am going to find out what is the work done, the small incremental work done because of this strip, and then we will integrate this strip, or we will move this strip right from this point to this. Means you have to integrate it for the entire process 1 to 2, and this is how we'll find out what is the work done, right? So when the piston moves an infinitesimal distance dl, in the previous diagram I'm talking about. So when the piston moves an infinitesimal distance dl, and if small a is the area of the piston, then the force F acting on the piston will be simply given as force will be equal to the pressure into area on measured acts. So F is equal to P into A, and the infinitesimal amount of work. When I say infinitesimal, it means on the elemental level I'm talking about, and the infinitesimal amount of work done by the gas on the system. Now why I'm saying work done by the gas on the system? Because the expansion is taking place, so work is done by the gas. So the expansion work, so the amount of work done by the gas on the system will be given by this expression. So elemental work I am representing by this symbol. So call this as a D cross or D dash, whatever you want to call it as. So I am saying, let us say D cross W. So W is for work, and this D cross W is for the elemental work. Hereafter I will not say cross. Whenever I say DW, it indicates that this symbol is included there. Fine. Why I am using this symbol, I will tell you in due course of time. Wait for some time. So the DW work, the infinitesimal amount of work done by the gas on the system, will be equal to the force which is acting here, force F, acting on the system or the piston, multiplied by the small incremental distance or infinitesimal distance dl. So this is we already know this P into A into dl, and now I am combining these two terms. The area A into the distance dl moved will give us the incremental volume, which is dV. So you understood what is dV from that diagram? So in short, what we did is we calculated what is the incremental work. This d bar w is given as PD, right? Now it is time to find out the total work done for the entire process 1 to 2. So the total work when the piston moves from position 1 to position 2 or state 1 to state 2, is given by this expression. So before this, you should write that w1-2 is nothing but the integral of this d bar w, integral of this, right? And then you get this expression. So w1-2 is equal to integral of p dv with the limits volume v1 to v2. So this is what the expression for the p dv were. Now I am intentionally writing this as w1-2. Why we are writing it like this? I will explain it in the next slide. Can I go to next slide?
Yes, sir.
Sir,
Yes,
1
sir.
minute.
No. So just write down the last expression. W1-2 is equal to integral the p dv with limits v1 to v2.
Yes, sir. Done, sir.
Now, the next concept which we are going to introduce is the path function. You may be knowing this, what is point function and path function. In some part of your physics, you must have studied this, but still it is time to revise it. So what is path function? Look at the diagram on the right hand side. So again, I am taking the PV plane or a PV diagram, and I am showing the state point 1 here, state point 2, and you can come from state point 1 to state 2 using the process which are given by these symbols A, B and C. So you can follow any path and still you can come to the final state, which is state 2. Any path can be followed, right? Now this is what is described here. So system can change its state from state point 1 to state 2 by 3 different processes. So I am naming those processes as 1A, 2, or you can simply say process path A, process path A, process path B, and process path C, like this, right? So when I use these kind of symbols, it means I am talking about the path followed by the process path. So the work done in all the process will be different. Work done in all the process will be different. Now why I am saying this, you have to go back and check the expression for the PDV work and look at that diagram, PV diagram, and what is the area under that PV diagram? Look at this, what is the area under this PV diagram? What is this area? This is nothing but work transfer. Getting me or not?
Yes.
Yes, sir.
So
Yes, sir.
if you change the path, the work transfer is going to change, right? So that is what the meaning of this line. Work done in all the process will be different. So now I am finding out what is the work done. I am just writing the expression, general expression from state point 1 to state point 2. So integral of this dw from 1 to 2 should not be written as w2 minus w1. This is not equal to w2 minus w1. Rather, it should be written like this. 1 to 2 of this dw should be equal to w1-2 is equal to 1 w2, or you can write it like w12 also. That's fine. Any of these symbols you can use, but you should not use these kind of symbols, w2 minus w1. Because work is a path function, it depends on the path followed by your system. So you do not have the absolute values of work at state point 1 and state point 2. There is nothing like W1 or W2. So the work W will come into picture whenever the process takes place, otherwise not. Is it clear? Hello?
Yes, sir.
Yes, sir. Yes, sir.
So work is a path function, it depends on the path followed by your system. So for this kind of functions, you should not write this integral dw is equal to w2 minus w1. Now the moment I said there is nothing like absolute values of w1 and w2, you must understand why I'm using this symbol. Because this is not completely differentiable. Now what is this not completely differentiable is there on the next slide. So can I go to next slide now?
Yes, sir.
Yes, sir.
Now let us talk about the point function. So what is point function? The function which does not depend on the path is called as a point function. Thermodynamic properties, all thermodynamic properties can be thought of as point functions because they have the definite value at a fixed state, right? I know that the atmospheric pressure is 1 atmosphere, or right now the temperature of the surrounding is 30 degrees C. So we have some definite value for thermodynamic properties at a fixed state, right? So thermodynamic properties are the point functions. Now, the change in thermodynamic property is independent of path and depends only on the end states. Now, this is important statement. The change in thermodynamic property is independent of path followed by your system, and it only depends on the end states. So I have the state, initial state 1, final state 2. So irrespective of by which way you are coming to the final state, the thermodynamic property changes happening in the thermodynamic properties are independent of this path. So they only depend on these two states. So as long as these two states are fixed, the change in the property is fixed, irrespective of which path you follow. Clear? So that's why they are point function. Now the differential of point functions are exact or perfect differentials. So if I say temperature T, now this is the point function. So I can write temperature change as a dt, right? This is definitely differentiable, right? Or perfect differential or exact differential I can use. Same is not true in case of work. Work is not the point function, it is path function, it depends on path followed. So I should use inexact differential like this. So this indicates inexact differential, or alternately you can use this symbol also, delta W. So this delta indicates inexact differential. Clear? So if you refer the standard textbooks, you will find that delta W is used, or this D dash is used to represent the inexact differential. So now, unlike the previous case where we have used this integral 1 to 2 of this d bar W should not be written like W2 minus W1. Here we are writing for change in volume dV. So integral 1 to 2 of dV can be written as V2 minus V1. Now why? Because this property has definite value at state point 2 and state point 1. So we know that the volume at this point may be 0.2 meter cube, and at this point it is 0.5 meter cube, something like that. So we have definite values. So you can write this V2 minus V1, right? And one more thing it is worth noting here. This is the symbol used for cyclic integral. So cyclic integral of dV will be equal to 0. What is the interpretation of this? Cyclic integral of dV will be 0. So if you have a system which starts from, let us say, the state point 1, it goes to point 2, again it goes to point 3, and it comes back to the initial state 1, right? So this is what is the cycle. So you are starting with some point and following all other paths, number of paths, you are coming back to the same initial state. So this is the cycle. So the cyclic integral of any point function like this, if you take, it will be equal to 0. So the cyclic integral of dV will be 0, cyclic integral of dP will be 0, or cyclic integral of dt will also be equal to 0. Note down all this.
Noted, sir.
Okay, very good. Now moving further, we'll run through the process. You may be aware of this. So shall I go fast? So PDV work in various quasi-static process. Now you know what is quasi-static process. So let us take the first process, which is constant pressure process. So the PV diagram is drawn, state point 1 to 2, the volume changes from V1 to V2, and the pressure is constant. This pressure is constant. Find out the work done, W1-2. So this will be integral PDV. So the pressure will remain as it is because it is constant, and the volume changes from V2 to V1. So that's why the dV will be replaced by V2 minus V1. So this is what the work done in the constant pressure process. Now look at the next process, work done in constant volume process. So show the PV diagram here. Then state point 1, state point 2. Now this time the volume remains constant and pressure changes from P1 to P2. But as the volume is constant, this dV term will be 0. So that's why the work done in constant volume process will be 0. Can I go to the next slide?
Yes, sir.
Yes, sir.
Now next process I am taking. So let us take the process, general process in which the product of this pressure and volume is constant. So PV equal to constant. So I am taking again the PV diagram. So state point 1, state point 2, and the law of this process is PV equal to constant. Right. Now our job is to find out what is the work done for this kind of process. So we'll always start with this W1-2 of integral P dV. Right. So this is our equation 1. Now what we'll do is we'll use the law of the process itself. So we know that PV is equal to P1 V1 is equal to constant, right? So this can be written as P2 V2 also. It doesn't make any difference. So this is our equation 2. Now what we have to do is we have to use this C here, convert this pressure in terms of volume, because you have to take integral in terms of volume, right? So you can replace this P by C by V here. Using that substitution, you can integrate the expression and you will get this equation at the end. So work done in process 1 to 2 for the process having law P equal to constant will be given as W1-2 is P1 V1 ln V2 by V1. Right? And in terms of, this is in terms of the volume ratio, and we know that law of the process is P1 V1 is equal to P2 V2, right? So from this I can say V1 by V2 by V1 is also equal to P1 by P2. So this ratio can be replaced by this ratio P1 by P2. So write down these two expressions. The work done in case of the process having law P equal to constant is given by either of these two equations. Noted?
Yes, sir.
Now next process will take the one more process having the law of PV raised to n equal to constant. That is also called as a polytropic process. Now look at the PV diagram. So we have the limits. Like I am taking here n is equal to 0, PV raised to n is equal to constant. So I have different values for n. So here n is equal to 0 and here it is infinity. And in between you can use the values n equal to 1, 2 or 3, something like this. And all the process you can draw in this, right? Fine. Now again, we have to find out the work done in this kind of process, polytropic process. So I am starting with the same expression, then I am writing law of the process, PV raised to n is constant, which is also equal to P1 V1 raised to n is equal to constant, so P2 V2 raised to n is equal to constant. Then following the same procedure, similar to the previous case, and integrate the expression, and you should get these equations for the work done. So you can note down the work done in process 1 to 2 for the polytropic process is given as W1-2 is equal to P1 V1 minus P2 V2 divided by n minus 1. So I am just rewriting this expression. We will be using this form of the equation most of the time and not the first one. So this equation is important for us. Now can I go to next slide? Mute yourself. There is some background noise. I should mute all. Done? Now take down the next process. Next process is the reverse. Next process is the adiabatic process. So law of the adiabatic process, I am using it as PV raised to gamma equal to constant. The symbol is gamma, this one. So PV raised to gamma equal to constant is law of this process. Now again follow the same procedure, and instead of n you have this time this gamma index, and you will get similar kind of expressions for the work done. So only thing is n is replaced by gamma. So note down this expression for the adiabatic process. So W1-2 is P1 V1 minus P2 V2 divided by gamma minus 1. Done?
Done, sir.
Apart from the PDV work, you can have the other kinds of works also. Now, what are those types of works? We'll discuss one by one. So I have included one slide for each kind of work. So we'll run through this. So What are the different types of works used apart from PDV work? So first is the electrical. Then we have the shaft work, then the paddle wheel or the steering work, the flow work, then the work done in extension of a solid bar, the work done in changing the area of a surface film, and at last the magnetization of a work done in magnetization of a paramagnetic solid. So these 7 types of works are there apart from your PDV work. So if I find out, if I want to find out what is the total work, so the total work can be combination of this PDV and any of these 7 work, right? Let us talk about the first type of work, which is electrical work. So how to find out the electrical work? So when current flows through a resistor, we know this. This time I'm taking the resistor as the system. There is work transfer happening into the system. So work is transferred to the system here. So this is because the current can drive a motor and the motor can drive a pulley, and we know this pulley can raise the weight. So it means this is nothing but the work as per the definition we talked about, right? So this is your resistor, then the system boundary is shown, the current is flowing through the resistor. So you know this from your electrical background, this current flowing through the system I will be equal to dc by d tau. Now what are those symbols? What is this capital C and this tau? So capital C is the charge in coulomb, we know, tau is the time in seconds, capital I is the current in amperes, and we'll be using the symbol E, capital E, for the voltage potential or the driving potential, right? So this dW, now incremental work I'm finding out. So dW will be equal to E into dc, where this dc is nothing but I into dt from this expression. So I'm just substituting for this I into d tau, not t, and then you can find out what is the total work done using this expression. So you have to integrate this this term, integrate this, and you will get the total work. So the electrical work is given by this expression, integral 1 to 2 of ei d tau. Note down this expression, and the rate of this work, rate of this electrical work is given by W dash. Now this dash indicates this is per unit time, means you have to divide this expression by time, right? So I'll be dividing it by d tau. So this d tau will get cancelled out, and this is how you get that the rate of doing the electrical work is product of this voltage into the current flowing through the system. Clear? Electrical work and the rate of doing the electrical work. Now the next type of work is nothing but the shaft work. So you are familiar with this kind of work. So what is shaft work? Now this time I'm taking shaft as a system. So the system boundary is shown here. So shaft is taken as a system. Now this is definitely kind of a work, right? Why? Because your shaft can rotate a pulley, and this pulley can raise the weight. So this is definitely the work. Now how to find out the work in this case? So you will write directly the expression for the total work W, which is integral of 1 to 2 of tau into d theta. Of capital T into d theta. Now what is capital T? Capital T is nothing but the torque, and what is d theta is the angular displacement, right? So the rate of doing this shaft work will be per unit time. So W will be replaced by W dash, and then you are writing this d theta by d tau term, and this d theta by d tau, this is nothing but the rate of angular displacement, which is nothing but the angular velocity omega. So this is how finally you can write the rate of doing the shaft work W dot will be the torque into angular velocity. Clear? So note down these symbols which we are using. T for torque, d theta is angular displacement, tau is time, and omega is the angular velocity. So this expression is important for us. Now, next is the paddle wheel or the steering work. Now look at the diagram. So we have a system like this. Let us say some fluid is there, and there is one fan here, or the stirrer you can call it as, and this is connected to this arrangement, weight arrangement using the shaft. So as the weight is lowered, if you lower down this weight, what will happen is the work is transferred into the fluid system. And how it is transferred to the fluid system? Through this the shaft, and the stirrer will rotate, and this is how the work is supplied to the system. So this type of work is called as the paddle wheel work or stirring work. Now how to find out this? So elemental work dW is given by the expression mz dz. So dz is the height by which you are lowering the weight. M into g is nothing but the weight which you are lowering, and this must be equal to the torque applied to the shaft, torque E, multiplied by the angular displacement d theta, right? So you can find out the total work in this case W as integral of this d bar W. So finally you will get this expression. So W is integral of 1 to 2 of T into d theta. Yeah. So this W dash is nothing but this term, weight of the weight which you are lowering. Now moving further, this is important type of work which we talk about in the steady flow energy system. So flow work. Now what do we mean by flow work? This may look pretty analogous to PDV work, but it is different than PDV work. So how it is? So the flow work is significant only in flow process or an open system. They represent the energy transferred across the system boundary as a result of energy imparted to the fluid by pump or a blower or by a compressor. So all these are what you can say, the devices which will push the fluid to make the fluid to flow across the control volume. Flow work is analogous to displacement work. Now look at the diagram on the left hand side. So we have this system, the system boundary shown by the dotted line, and there are two sections. So this is inlet section, let us say section 1, and this is section 2 is the outlet section. So some mass of the fluid is entering from this side and it is leaving from this side, right? So what we will do is we will imagine that there is some kind of a piston here. So this is the imaginary piston, and then there is this change in volume, the incremental change in volume dV happening at the inlet section, similarly happening at the outlet section. And this is as good as imagining that some component is there here at this location, which is pushing the fluid through this passage. So that type of we are assuming. So the flow work will be calculated like this. So this d bar W flow, incremental flow work, will be given as PdV, right? So I am expanding this term further. So PdV, so dV is replaced by VDM. So we know that the specific volume is defined as dV by dm, right? So from this I can write this dV is equal to VDM. So same thing I am doing here. Now this is a general expression for the elemental flow work d bar W flow. So I can apply this at the inlet section, which is here. So I will write this d bar W flow in. So this is the pressure volume at the inlet, that's why pressure in specific volume. So I will write P1 V1, and this is the mass dm1 at the inlet. So this is the incremental mass dm1, the total mass is m1, right? I can write what is the mass flow rate through this inlet, let us say. So mass flow rate is nothing but the rate of change of mass per minute time, right? So instead of using W, I will be using symbol m dot 1. So m dot 1 will be given as A1 V1 upon small v. So this is volume and this is specific volume. So this is also nothing but dm1 by dt. So call this as a time t and not a tau. So dm1 by dt is the mass flow rate m1 dot. So I can write this expression dw flow in which is p1 v1 dm1, and similarly I can write the same expression for the work done at the outlet here. So it will be given as P2 V2 dm2, where dm1 is the mass entering at inlet 1 and dm2 is the mass, elemental mass exiting from this outlet 2, right? So if I want to find out what is the flow work per unit mass, so I'm writing it here, flow work per unit mass. So I have to take this mass on the left hand side. Then if I divide this dW by dm, this term indicates the flow work per unit mass. So the same expression can be written like this. So dW, this W flow is equal to P into V. So pressure into specific volume. So this is flow work per unit mass. Remember this. This is per unit mass. So if your work is measured in, let us say, joule or kilojoule, then this work per unit mass will be measured as joule per kg or kilojoule per kg. So it is per unit mass. This is, remember this. Clear? Now can I go to next slide? Hello?
Yes, sir.
Okay, fine.
Yes,
Now
sir.
next is work done in extension of a solid bar. Now look at the diagram and see how it is related to this description. So what we are doing is we are considering a system in the form of a solid bar like this, and you are applying some force to this bar and you are trying to extend this bar, right? Extension of the solid bar. Now the bar is fixed at this position, right, to this plate. And you are applying the force F at this end. Let the force be represented by as force capital F is given as sigma into A, right? We know this. Where this capital A is nothing but the cross sectional area of your bar, this one, and sigma is the normal stress. So you can find out what is the work done in this situation. So you will write the expression as this W is equal to minus of integral sigma A dx. The limits of integral will be x1 to x2, right? So x1 is the this value and x2 when it is extended, right? So you note down this formula. Now what is the significance of this minus sign in this expression? So the minus sign is required because work is done on the bar when dx is positive, means when the expansion will take place, means length of this bar will increase, but dx is positive in that case. So length is increasing, it means the work is done on the bar, and our system is nothing but the bar. So this is our system bar. So that's why this negative sign is required. Moving further, we'll talk about one more type of work done in changing the area of a surface film. Now look at the diagram and the paragraph which is given along with the diagram. So what you see here is there is a film on the surface of liquid, and it has the surface tension property, right? So what is done is you are applying force F here and you are trying to stretch this film in this direction. So this part is movable wire. So what will be the work done in this case when you are trying to stretch this film, right? So this will be given as dWs minus sigma into dA, right? Where this sigma is surface tension, note down. Sigma is a surface tension in this case and not the stress, otherwise you take it as stress. So this is surface tension. So surface tension is basically the force applied per meter length. So unit of sigma will be Newton per meter, force applied per meter length. So this is for elementary, and the total work done W will be equal to minus integral 1 to 2 of sigma dA. Now you know the significance of minus sign because the work is done in the system. That's why minus sign. Now the last part of work other than PdV work, or the last type of work, the magnetization of a paramagnetic solid, or work done in magnetic solid. So you can write down this, the work done per unit volume on a magnetic material through which the magnetic and magnetization fields are uniform. You can write down this expression, dW is minus h into di. You may be knowing these symbols. What is h? H is nothing but the field strength. Then the di is nothing but the component of the magnetization in the direction of the flow field. This is for element, and the total work done in magnetization will be given by this expression. W1-2 is minus integral I1 to I2 or HDF. HDF. Again, the significance of the minus sign is here also the work is done on the system. So that's why minus sign must be there. Done. So that's all about the different types of works other than PDV work. So as I said before, the total work can be the sum of any of these 7 types of works and the PDV work, along with PDV work, these 7. Right? Is it clear?
Yes, sir.
Sir, can you show the slide of change of area one?
No?
Changes the area, surface tension one.
This one. Okay. So here
Okay,
note
sir.
down sigma is surface tension. Surface tension. Now, moving further, we'll talk about the free expansion process, and this free expansion process happens with zero work transfer. So I am making the statement well in advance that the work done in free expansion process is 0. So if I say this integral of dW or integral PDV is equal to 0, this is what I am saying well in advance. This free expansion process is the zero work transfer process. This is what the statement I am making. Right? Now what you have to do is you have to look at the combination of the systems using this box and try to connect this to these 5 diagrams, and then think about why free expansion is a zero work transfer process. If you understood the definition of work, you should be in position to explain this. Fine. So look at the first case. Consider the gas and vacuum together as a system, which is shown in diagram 1. So I have a system which is shown by this dotted line. In one partition there is gas and the other is vacuum, and in between there is one partition here. Partition is there. Now what you have to do is, and this is insulated from the surrounding, that's why this boundary is shown here. Insulation is shown. So what you have to do is you have to take out this partition and allow gas to expand. So this is the first experiment we are talking about. So neglect the resistance offered due to the removal of this partition. So ignore what is happening to the partition. So just take out the partition and allow the gas to expand. This is the first scenario. So do you think there is work involved in this process when the gas expands? So there is no work transfer. See, if you look at this expression, there is no work transfer. Why there is no work transfer? Because gas is simply expanding against the vacuum, and vacuum is not providing any kind of resistance, right, for this expansion of the gas, right? And your initial system, which was this, again it is remaining one and the same. So there is no change or no work is involved in this process when the gas is expanding against the vacuum, right? Because nothing is crossing the boundary. See, where is your system boundary? Your system boundary is here itself, right? Right from the beginning to the end, your system boundary is one and the same. And what we talked about work is a boundary phenomenon. Note down somewhere, work is a boundary phenomenon. So nothing is crossing the boundary in this case. So there is no question of this work done in the free expansion process. Nothing is crossing the boundary. First case. Now what about the second? Now what we'll do is we'll consider gas as a system alone. So look at the diagram 2 now. So again that partition is there, vacuum on the right hand side and the gas on the left hand side, right? But this time, instead of considering the whole system as a system together, gas and vacuum, this time I am considering the gas alone as a system, right? And then what I will do is I will take out this partition and then allow the gas to expand. Now this time you may say that the gas is crossing the boundary here, right? And then you can think about solving this integral PdV, right? But remember, the moment you take out the partition from here, what you know is only the initial state, which was before you take out the partition, and once you take out the partition, the gas will expand all of a sudden, and you will reach the state 2, which is again the final equilibrium state. So what is happening in this case is the in-between data is not available. You cannot trace the states in between, because this is when you take out the partition, the expansion of the gas against the vacuum is not a quasi-static process. Note down somewhere. So expansion of the gas against vacuum is not a quasi-static process, so you cannot show this process or trace this process on the paper like this. So you know only initial and the final equilibrium state. You cannot have the history in between. And integral PdV is evaluated only for quasi-static process. Note down this. Integral PdV is evaluated for quasi-static process and not for this kind of process where the history in between is not known to you, right? So what you will do is now those who are still thinking that there is some work transfer is there, so they may think the third option. So let us consider the gas as a system and divide the vacuum using the partitions. This is what they may think. So look at this diagram, diagram 4. So we have this gas as a system similar to this. Now what is done here is this vacuum is divided into the small partitions like this. So you can have the partitions. Now this is exactly similar to what we studied in quasi-static process. So you know the microwaves we took out one by one from that experiment of piston cylinder arrangement, right? So similar kind of thing is happening here. So I am using large number of partitions here, and what you have to do is you have to take out one partition at a time. So if you do the experiment in this way, then you may think that I can trace the in-between states also, because all states will be in equilibrium. So I can represent this process path using this continuous line. This is what you may argue. Correct? Now the question arises, but still, is there any work involved in this process? The answer is no. Still the work transfer is zero, because when your gas is expanding, it has to overcome certain resistance or some kind of resistance. And in this case, vacuum does not provide any kind of resistance for the expansion of this gas. So even though you may trace all the states in between, and even though you think that PdV integral can be solved, the reality is the work transfer is zero, because your gas is simply not overcoming any kind of resistance while expanding against the vacuum. So in short, based on these 5 diagrams and whatever we discussed at the end, we conclude that the free expansion is the process with zero work transfer. Clear? Hello?
Yes, sir. Clear.
Okay, fine. Now next, heat transfer or simply heat. So what do we mean by work we define? Now what do we mean by heat? Take down the definition of heat or heat transfer. So heat is defined as an energy in transition. Now these words are important. If you miss these two words, energy in transition, it is transferred across a boundary by virtue of a temperature difference. So these two things are important in definition of heat transfer. Energy in transition, and it is transferred across the boundary, and while it is transferred across the boundary, what is the driving potential for heat transfer to take place? It is the temperature difference. So heat is a form of energy in transition, and the heat transfer occurs across the boundary, and it occurs because of the temperature difference. Clear? So this is the definition of heat. Now you can note down what is the sign convention we are supposed to follow for heat transfer or heat. So this is your system, and this is heat supplied or heat, you can say heat rejected by the system, and this one is heat supplied to the system. So our sign convention is heat rejected by the system is taken as negative and the heat supplied to the system is taken as positive. So the sign convention for heat is exactly opposite to the work. So we know work done by the system, this is work done by the system is positive, and the work done on the system is negative. Correct? So this is positive, this is negative. So you can see that the sign convention is opposite for heat and work transfer. Note it down, sign convention.
Yes, sir.
So this last line is important. So heat is a boundary phenomenon. As we talked about this, it happens at the or it crosses the boundary. The unit of heat is joule in SI system, and the rate of heat transfer means per unit time. The heat transfer or the rate of heat transfer is given in watt or kilowatt. So it will be joule per second or kilojoule per second, right? Watt or kilowatt. Done? Now heat transfer is a path function. Now why it is path function? The amount of heat transfer when a system changes from state 1 to state 2 depends on the intermediate states, means it depends on path. So amount of heat transfer depends on the path, so it is a path function. So this dq is an inexact differential, so I should not write dq rather than this, I should write it like this, right? So here is the notations I am using. So integral of 1 to 2 of this d bar q or d cross q should not be written as q2 minus q1, because you cannot have absolute values of q at state point 2 and state point 1. So it should be written like q1 dash 2, 1 q2, or simply you can write q1 2. That is also fine, right? Yeah. So heat transfer is a path function. Work transfer is also path function, right? So heat and work both are path function. Can I go to next slide?
Yes, sir.
So work and heat transfer in quasi-static process. Now this slide is important. Whatever we have talked about in last 2 lectures can be summarized in this single slide. So look at the diagram, the PV diagram, and the work done, how to find out the work done, which is nothing but the area under this curve. Area under PV diagram is nothing but work transfer. So you should remember this. Area under PV diagram is work transfer, and how to find out the work transfer? W1-2 is integral PdV. Similarly, the area under another curve I am taking. So this is again the similar kind of curve, but the area is different. So I am taking the temperature on the y-axis, but I don't know what is the property on the x-axis. So I simply I'm simply using the capital X as a symbol, and this area under this TS plot is nothing but the heat transfer. So q1-2 is the integral of d bar q, which is also integral of t dx. So what is this x quantity we are going to introduce in second law of thermodynamics? So what is there on this axis? This x property we are going to introduce in second law of thermodynamics. So that is nothing but the entropy. I am telling you well in advance. So you can note down this: the area under PV diagram gives work transfer, and area under the TS diagram. So this x will be replaced by the entropy later on. So area under TS diagram is heat transfer, Q. So that's all about the introduction to the thermodynamics. Now I have only one slide at the end. We will cover that and then we'll stop. Is it okay if I extend the lecture maybe by 5 minutes?
Yes, sir.
Yes, sir.
So now we will solve. Bolo. No, go ahead.
Nothing, sir.
Okay. So we will solve the first problem. This problem will really test your understanding of the basic concepts, whatever concepts we talked about right now. Now pay attention to this problem. So imagine you have the situation like this. So these are the clouds, and the problem statement is the rain is falling from the clouds. You can note down. I am not writing the statement on the screen. So rain is falling from the clouds at the rate of 10 meter cube per second. The rain is falling from the clouds at the rate of 10 meter cube per second. Find out the amount of rain collected on the ground. Find out the amount of rain collected on the ground after 50 seconds. So this is your ground. Got it? It's a very simple problem. So rain is falling from the clouds at the rate of 10 meters per second. Find out the amount of rain collected on ground after 50 seconds.
meter
cube. 500 meter cube. Any other answer? Or all of you settled with this 500 meter cube? Done? Now pay attention to the problem. The rain is falling from the clouds at the rate of 10 meter cube per second. Find the amount of rain collected on the ground after 50 seconds. Answer is 0. Hello, are you getting me or not?
Yes, sir.
Now why the answer is 0? Why the rain collected on the ground is 0? See, what is the state of the water present in the clouds? Whatever it may be. Whatever it may be. But it is definitely not rain. Correct? Getting me or not? So whatever may be the state of water present in the clouds, we do not call it as a rain. It may be whatever you want to name it, fine. But it is definitely not rain. Do you agree or not? Yes. Similarly, when this rainwater, when this rain falls on the ground and touches the ground, do we call this as a rain? We call this as a rainwater and not rain. So we call it as a rainwater. We do not call it as a rain. So what I asked you, find out the amount of rain collected on the ground after 50 seconds. So now try to understand the analogy between rain, work and heat. So heat and work are path functions, right? And they only come into picture when they cross the boundary, right? So whatever the state of the water present in the cloud, we do not call it as a rain, right? Now, moment it crosses the boundary here, we start calling it as a rain, right? And up to what point we call it as a rain? The moment it touches the ground and enters another system, right? So up to this point we call it as a rain, and the moment it touches the ground, again we call it as a rainwater and not rain. So what is rain is in between, right? So same is true about work and heat. So work and heat are in between. The moment it crosses the boundary, we start talking about the work transfer or heat transfer. I hope you understood this or not. Now try to connect this. Work is a boundary phenomenon, or heat is a boundary phenomenon, heat transfer and work transfer are boundary phenomena. They only come into picture when they cross the boundary. Are you getting my point or not? कितने लोगों को समझ में आई है?
Understood.
So hereafter you will not forget what is point function and path function. So always remember this work and heat transfer are pretty analogous to rain. So I think we should stop now. So next lecture I am going to start the first law of thermodynamics. Just let me download the attendance and then we'll stop.